Alrighty, 27.19. In an experiment with cosmic rays, a vertical beam of particles that have a charge of magnitude 3e and mass 12 times the proton mass enters a uniform horizontal magnetic field with a magnitude of 0.25 Tesla and is bent in a semicircle of diameter 95 centimeters as shown. Find the speed of the particles and the sign of their charge. Alright, so first things first. We are moving in a circle, which means we have centripetal acceleration. So anytime you see a particle moving in a circle, it's probably a good hint you're going to be using some circular motion equations. So the particles are moving in a circle. The centripetal acceleration, v squared over r. And then we can turn that into a force by multiplying by m. And the force that's causing it to move in a circle is our magnetic force, QV cross B. So because our velocity and our field are perpendicular, we can just write QV times B. So one of our V's cancel out. So we have mv over r equals qb. We're looking for the speed. So v equals q b r over m. So the speed of our particles is q, which is 3e. So it's 3 times 1.602 times 10 to the minus 19 coulombs. B was 0.25 Tesla. R was 0.95 meters. That's the diameter, so the r is divided by 2. And the mass is 12 times the mass of a proton, which is 1.67 times 10 to the minus 27 kilograms. Right? Yes. Okay, cool. Okay. So, if we stuff that into our handy dandy calculator, we get 3 times 1.602 times 10 to the minus 19 times 0.25 times 0.95 over 2 divided by 12 times 1.67 times 10 to the minus 27. Guess what? So the speed of our guys is 2.85 times 10 to the 6 meters per second. Those dudes are moving super fast. Now to find the direction, we come to our handy dandy right hand rule. So this is my first vector, QV cross B equals F. So if I line this up with my notebook, my force is pushing the dudes left, so my force is left. My B is out of the page. So force is left, B is out of the page, and QV is going to be this one. So because QV is pointing in the opposite direction of what the picture shows, that means I have negative charges. Cool. All right. Part B. Part B, is it reasonable to ignore the gravity force on the particles? So if we look at the force of gravity on these dudes, force of gravity is mass times gravity. So our mass is 12 times the mass of a proton, which is 1.67 times 10 to the minus 27 kilograms, times g, which is 9.81 meters per second squared. So the force of gravity on these dudes times 9.81 is 1.97 times 10 to the minus 25 newtons. Holy dang, that's super duper small. And if we look at our force from our magnetic field, which was QVB, our Q was 3 times 10, 3 times the charge of an electron, so 3 times 1.602 times 10 to the minus 19 coulombs, times our velocity, which was 2.85 times 10 to the 6 meters per second, times B, which was 0.25 Tesla. So if we plug that in, 1.602 times 10 to the minus 19 times 2.85 times 10 to the 6 times 0.25. Oh my god, I cannot write today, I'm so sorry. 3.4 times 10 to the minus 13 newtons. 10 to the minus 13, 10 to the minus 25. Really small, a hell of a lot smaller. This one wins by a lot. This one is negligible. Way tiny. Nope. Negligible. So we don't really care. In part C, how does the speed of the particles as they enter the field compare to their speed as they exit the field? So, force from gravity is negligible. It's not going to do anything to make those particles speed up because they're itty bitty and they're already traveling super duper fast. Our magnetic force is perpendicular to the path. So if you remember, work equals force dot distance. If I have a dot product of two perpendicular things, that gives me 0. So the work done by a magnetic force is always 0 because it's perpendicular to the path. So work by FB always 0, which means it's not going to do anything to change the speed of the particle. Because if there's no work done, there's no change in kinetic energy. No work, no change in kinetic energy. No work, no speed change. Okay? So the speed that you leave the field is going to be the same as the speed you entered.